Okay, so now you've watched videos on how to set up ice tables. You've watched videos on how to calculate Q and what the heck you're supposed to do with figuring out which direction a reaction goes. Now what we're going to deal with right now is some really tricky problems. Now, dun, 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 it's showing you on this slide right here a sneak preview of the fact that you absolutely, there's a very small number of times that when you're working through problems that it's not a perfect square. It's not easy to just cancel things out and so on. And you're going to have to use the quadratic formula. And it really sucks and it's not really fun. Personally, actually, I think it's fun. I think it's really tedious, but I think it's really kind of neat that everything falls into place. However, I am a chemistry teacher and I have kind of a sick math mind. So I'm going to go through how to do this tricky problem with you, just so that you feel that you are comfortable and confident with how to work through this. But sometimes you're just going to have to use the quadratic equation. Now, key here is this. You will never have to use the quadratic formula in the AP test. So if you ever get to a point where in the AP test you're doing an equilibrium problem and it comes to having to use the quadratic formula, you know you've done it wrong in the AP test. So you don't have to do it using that in the AP test. Also, I do know that some of you do have the quadratic equation in your calculators. So once you get the numbers for the quadratic formula, you can throw them into your calculator and it'll give you some values. So that's kind of a couple of pieces of information there for you. So this problem here is that we have an equilibrium mixture and it's found to have 0.60 moles of one, 0.40 moles of another, 0.80 moles of another, and 0.10 moles of another. So it tells you the equilibrium of this substance. So it is at equilibrium and it says calculate the Kc. So the first thing that you're going to want to do is you're going to want to calculate the Kc. You're like, but Ms. Schneider, stop. You told us that in the last video we're not allowed to put moles in ice tables, but you'll notice it says per liter. So 0.60 moles is really 0.60 molar, and so on. So we're going to first calculate Kc because that's what it tells us to do at the beginning. So the first thing that we need to do is Kc equals, and then we're going to put, so we need products of reactants, so that's NO, SO3, oops, and all those are in a 1-to-1 ratio, so nothing has to be raised to any power, SO2, NO2. And then you're just going to plug those numbers in. So you know that 0.60 is SO3 and 0.4 is, so 0.40 molar times 0.60 molar. Plug that in, and you've got 0.80 molar and 1.0 molar. And that, my friends, if you use your calculator, equals 3.0. So it told us to calculate the Kc. Now, it says, once we've calculated the Kc, and remember that is a constant, once we've calculated the Kc, 1 more mole of NO was forced into the vessel. Dang. So what that does is that screws up the equilibrium. That shoves the equilibrium in a different direction. So the first thing that we have to do is figure out which direction it's going to go. If I add NO to it, and NO is on the product side, then it is going, and it's already in equilibrium, and now I've added 1 mole. What that means is it is going to shift it to the left. So when we write our ice table, you need to know that it's going to shift it to the left. So that's what we're going to do right now is we're going to write out an ice table. So the first thing we have to do, of course, is write out the reaction, SO2 plus NO2. And I am going to skip the phases here. They're all gases. You should never skip the phases. And I'm only going to skip the phases because my pen is not working as well as I want it to. So we know that this is going to start out, ICE is going to start out at 0.80 molar. We know that NO2 is 1.0 molar. See, this is what I'm talking about. NO, remember, it started out at 0.40 molar, but we added 1 mole. So it's now 1.40 molar. And SO3 is 0.60 molar. So The change here is this. We know that the reaction is going to shift in this direction because we added some to the products. So we know that this is going to be plus X, this is going to be plus X, oh, come on, minus X and minus X. And they're all 1X's because it's 1 to 1 to 1 to 1 ratio. So that's what we're going to do now. And then we're going to write out 0.80 plus X, 1.0 plus X, 1.40 minus X, and 0.60 minus X. So that gives you some information there. Then when we're writing out our new balance or our new K equation, we've got K equals, and it's products 1.40 minus X, 0.60 minus X over 0.80 plus X, and 1.0 plus X. Now, what you're going to notice right away that's different from the ones that we've done before is that this is not a perfect square. Dun, dun, dun. So what we need to do is we need to simplify all this so that we can get it into our quadratic formula. I have done that for you. I think that it is a great thing for you to go through and try it at least once to try to figure out whether you can get the work that I did and if you can follow all of the intricate details of that. So if you want to pause and try to solve this by doing foiling and then combining like terms, do that and then flip it over to the next part and I will show you what the actual work looks like. So now the actual work, there's our ice table. That's all the stuff we already went through. But here is now the work of trying to figure out the quadratic formula. So I took my initial K equation right up here, and I then did FOIL here. And then I combined like terms here. And remember, we know that it equals Kc, which is 3.0. We solved for that initially. Then I take this and I multiply the whole thing by 3. That's what I did right here. And so I have one side of the equation is 3 times that. And the other side of the equation is the rest of the stuff that was on the top here. Or excuse me, right here with combined like terms. And then I start multiplying through the 3 and I combine like terms and then I adjust it so that just like normally when you see a quadratic formula, you have the x squared at the front and so on. So this is now our a in the quadratic formula. This is the b in our quadratic formula and this is the c in our quadratic formula to solve for x. Now, then I said, plug it into the quadratic formula. Remember, this is the formula for the quadratic formula. I did not show that in this video to show you how to plug those in. Figured you could do that yourself. Now, the key here is that x can never be negative. So you're going to get a negative and a positive value. The negative value doesn't make any sense for this stuff. So please do not keep the negative value because that doesn't make any sense. So then once you have solved your quadratic formula, you should pause it, make sure you get the answers, and click play, and I will show you the correct answers. So here are the correct answers that you should have gotten for moles and for molar, right? Because it's in a 1 liter container. So this is your correct answer for what each of the new molarity, and then because it's in a 1 liter, the number of moles of each of the substances at equilibrium. So that is probably one of the most difficult types of problems that you will see, just because it's really tedious and intense in terms of all the different little moving pieces. But nothing's different than anything else that we've done. It's just adding that quadratic formula layer to it. But once you figure out x, and hopefully your quadratic formula showed you that the x was 0.12. Once you figured out that x, then you plug it into our back into our ice table here, and we know that the equilibrium for SO2 is 0.80 plus x. Well, if x is 0.12, then our SO2 is 0.92. So hopefully that makes a little bit more sense on how to do the most difficult type of problem. Okay, so last thing and the last piece that I think is going to make things a lot easier is this kind of problem. Sometimes you might think you want to use the quadratic equation because they're not perfect squares or whatever. However, if k is really small, and it's kind of a little bit of a flexible rule of thumb, and I'll show you how to check that in just a minute. But if you use the k being something 10 to the negative third or smaller, and a lot of times our k's in this case are 10 to the negative third or smaller, then what we can do is we can actually assume that the stuff that is reacting is going to be small enough that it will not affect the overall calculation. So I'll show you how that works in a second. First thing I want you to do is I want you to write out an ice table, please. So go ahead and do this ice table now that you're feeling hopefully a little bit more comfortable with the ice tables. So, oops, that's the answer. We don't want the answers. I hoped that there was an ice table there, and there is not. So you've got a 0.50 molar sample of NO and none of this and none of this. We know that the reaction must go in the forward direction because we don't have anything of the NO or the Cl2. So now we've got to take this, and this is a plus 2x due to the 2 here. And this is a plus x due to the 1 here. This is a minus 2x due to the 2 here. Now, what we're going to do is we're going to say that this is 0.50 minus 2x, this is 2x, and this is x. And so when we're writing out our k equation, and in this case, because it's molarity, this is Kc, equals 2x squared times x all over 0.50 minus 2x squared. Now, when we combine like terms, 2x squared is 4x squared and times x, and that makes this 4x cubed. And this is 0.50 minus 2x squared. So what happens here is if we know that our k, and in this case our k is 1.6 times 10 to the negative fifth, that is smaller than 10 to the negative third. When that happens, what we can do is we can take this specific 2x right here. And what we're saying is that if k is really small, the reaction is not going to produce a lot of products, is what it's saying. And so the reactant, the 0.50 molar here, is going to go down a very small amount. It's a lot like our bleach kinetics lab that we did, where we made the concentration of the bleach so high that the reaction with the dye didn't really reduce the concentration very much. And so that's what we're doing here is we're saying, okay, we're making such a small amount of the NO and the Cl2 that we can assume that this is negligible on the bottom only. So we still have to have something to solve for. So then that makes things a lot easier. If we have the equation 1.6 times 10 to the negative fifth equals 4x cubed over 0.50 squared, we now have just one variable in one place, square the 0.50, multiply it by 1.6 times 10 to the negative fifth, divide by 4, and then take the cube root. And guess what? Now you've got x equals 0.010. Now you can plug that 0.010 in there. And here's the kicker. You've got to plug it back in there now that you know. Okay. So your final answer for those questions are that 0.50 minus 2x is 0.48, 2x is 0.020, and x is 0.010. Now, going back to that's the answer. Now, because we want to avoid the quadratic formula, since the k is so small, we can assume that the reaction will not go far in the forward direction, and that x will be very small. If x is very small, then 0.50 minus 2x can be approximately equal to 0.50. And so what we've got this, it is approximately 0.50 is what I want you to see here. Now, we've got to check that. We've got to make sure that we're checking the information because there's this thing called the 5% rule. And AP will check to make sure that if you make the assumption that our 2x in this case is small enough to ignore when we're doing the calculation. It has to be below 5% of the initial concentration or initial pressure. So you have to check to make sure that your 5% rule is correct. I'm going to actually show it out here instead of in that little box. You can put it in the little box if you want to, but here's what you're going to do. So what is 2x? 2x in this case is 2 times 0.101. And we need to divide that by our initial. So here's the real story is that you've got to figure out if whatever you're subtracting is less than 5% of whatever you're subtracting it from. So if pretend this was like 0.40 minus 4x, I don't even know, then your 4x here would have to be less than 5% of your 0.40. That's what you need to do. So that's where these numbers are coming from. That's why I got the 2x here, because the 2x is what we're looking for in this specific problem. And the reason I have the 0.50 is due to the fact that that's the initial. If the initial was something else, we would put something else in there. And then you multiply it by 100. And you figure out if that answer is less than 5%. If you did the calculation right, it should be 4%. Come on, percent sign, and that is good to go. Yay. Okay, now if that is not good to go, let's say you got 6% or 7% or 8% or something, guess what? You can't make that assumption. You have to go back and you actually have to use the quadratic formula. Dun, dun, dun. So you don't want to have to do that, but if you must, if this comes out higher than 5%, then you know that your assumption was not, or your approximation was not reasonable, and therefore you need to go back and you need to do all the quadratic formula steps. So the last thing is one more for the fun of it so that you can practice all of the stuff that you're doing. Go ahead and go through this problem, and then I'll flash up the answer to it. When you're finished with going through it, it wants you to write the KP expression. The one key here is that you'll notice this is solid. So when you're writing out your ice table, that doesn't really show up in your ice table for your equilibrium value, because it is a solid and it will not show up in the equilibrium expression. So go ahead and try that out. This is another kind of tricky one, due to the fact that we do have that solid in there. So go ahead and try it and then go through the answer document. I will start explaining the answer document as soon as you finish it up. So you'll notice here that we actually did put something in here for the solid. What you have to understand here is that it's in quotes because this is in grams and we know that this is moles, right? We know that the X is stoichiometrically part of moles. What we're doing here is we're just doing it so that you can see that the reaction is going to go in the forward direction, obviously because we don't have any NH3 or HI, and to get you kind of the relationship between the X and everything like that. Also, you don't really have any other information about what these are, and so you need to use it somehow. So it says 10 grams was sealed and so on, and so go ahead and go to the next slide, and you'll see that we leave that in there, but we do know that the KP equation is pressure of NH3 times the pressure of HI. We know that both of those are going to be the same due to the fact that both of them are X. So we know that this is X squared. We also know that the KP in the problem is actually given to you, and that is 0.215. So to solve for what each X is, you just have to take the square root of both sides, and you get that each one is 0.464 atm. So that will tell you which pressure for each of them. Now, the question asks not what is the pressure for each of them, but what is the total pressure in the flask? Total pressure in the flask is this plus this. So it's 0.464 times 2, or 0.464 plus 0.464 to give you the total pressure of the flask at the equilibrium, which winds up being, of course, 0.928. When you put all that together. The last one asks you to figure out, excuse me, 0.928. So the last part actually asks you to figure out how many grams of NH4I you have left at the ends. Now, We know that if you look for, first of all, you know that you can't put solids into the ideal gas law. You do have lots of other information. So if you're just looking at NH3, you know that the pressure for NH3 was 0.464. You know that the volume of the container is 2 liters, and you know that the temperature was 673 Kelvin. So if you plug that in, you know that you created 0.0168 moles of NH3. Why is that important? Well, if we go back to, remember we put those little quotation marks because this right here is not necessarily 10 grams minus whatever X we got. We have to solve for this specific X because this is grams and this is moles. So what we did was we figured out how many moles were each of these, right, that were created. And then from that, you use stoichiometry to figure out how many grams we lost of the NH4I. Once we figure out how many grams of NH4I was lost, we can plug that back into what we had available, and that's how we figure out the remaining amount of NH4I at the very end. So hopefully that helps you to figure out how to do all this specific problem. It's another it's another difficult type of problem due to the fact that the X that's here is not a mole X, but we need it to be a mole X over here. So hopefully you figured out, you were able to see how we utilized all of the pieces of information here. This is this right here is a mole X. We plugged it into the KP because each of them are equal, and solved for the pressure that way, due to the fact that our KP equation is just pressure of NH3 times pressure of HI, which is X times X, which is X squared. And then because you cannot put a solid into the gas law equation, that's why we get the information that we get here with the NH3. And then once we get the NH3, use plain old stoichiometry to get to how much of the NH4I we used up, and subtract it from what we had initially to give us our answer. Hopefully this helps you. And you're feeling a little bit more comfortable with ice tables and doing the calculations. And if you have any questions, please feel free to email your teacher or bring in your questions when you get back.